thinking, Travis?
You're
not necessarily wrong.
I was thinking something. Does that have something to do with light being separated into its component wavelengths?
Okay, but why is it separated into its component wavelengths? So yes, you're right, but why is that happening? Why do we see those specific lines for different elements? Okay, so you should be looking at figure 7.10, that right-hand corner. What is that picture telling you? Do you understand that picture? So we have the nucleus, and you have those orange circles. What are those orange circles? N equals 1, N equals 2, N equals 3. What are those? They're not neutrons. Okay, the green things are the electrons. What are the N's representing? What are those circles representing? Do you remember you have a thought?
For what N stands for? Would be the principal quantum.
Yes. What's our principal quantum number tell us? Remember, Jillian? Big idea. What's the principal quantum number, Anna? The energy level. Okay, so again, coming back to the question, why do we see those specific lines of light? Do you connect the dots with the picture? What are the electrons doing that's giving off the light when you're looking at an atom? Do you have a thought, Travis?
Well, I had another idea, but is that to do with frequency?
Okay, the frequency of the waves give us the different colors. So, yes, that's why we have the different colors of light. What are those electrons doing?
Giving off stuff.
Why are they giving off stuff? They're giving off the light, yes. That's why we see those colors, because the electrons are giving off the light. Why are they giving off the light? What is the picture showing that they're doing? They're moving. More specifically, they're doing what?
Orbiting.
They're jumping. Well, okay, they are orbiting, but not only are they orbiting, they're jumping from what?
Energy level.
From an energy level to a lower energy level. So we're talking about the orbit this time, the circle, okay? And when they're jumping, they're going back down to their lowest energy state. What's that called? Ground state. They were what?
Excited.
So they were excited. In order to jump down, they had to give off energy. And how do we know they gave off that energy? The light that we see from those electrons jumping down. So when they jump down, they have to give off some form of energy. And based on where they're jumping from, is giving those different frequencies, which are giving us the different colors. So you have ultraviolet when the electrons are moving from the 7th all the way down to the 1st. So if they're moving down to the 1st energy level, it's ultraviolet light. What do we know about ultraviolet light compared to visible light? We know about the frequency of it. Travis, you remember?
It's higher.
It's a lot higher. So you have a higher. They're jumping further, so they're giving off a higher frequency of light. Whereas, notice your visible light spectrum, they're jumping to your 2nd energy level, and depending on where you're jumping from, they're going to give you that array of colors. So red, orange, yellow, green, blue, violet, when they jump down to the 2nd one. Or infrared if they're jumping down to the 3rd one. So big idea, why do we see that line spectrum? Why are we seeing that through a spectrometer? The electrons are? Be a little bit more specific. Jumping each energy level and giving off light in that process, going from that excited to that ground state for that. That's why we see a line spectrum, and that's how we can identify which element it is because of their electron configuration. What does that mean? What is electron configuration? Remember, Brian? Remember, Megan? What page are you on?
Page 105.
Page 105. What is the electron configuration? What is it, Megan?
The complete arrangement of electrons in an atom.
So where they're arranged is going to determine when they're excited what they're going to jump from and give off those colors of light as well. Okay, so keep going. Number 8. What is the primary difference between the Bohr model of the atom and its predecessor, the Rutherford model? Well, what is the name of the Rutherford model? Do you remember, Brian?
That's a nuclear model.
Okay. Planetary was another name. So nuclear, planetary. Ben, you know?
Well, the Bohr model included a nucleus.
Say that again?
The Bohr model included a nucleus.
So does the Rutherford model.
Well, I mean, not a nucleus. It's like protons and neutrons, not just like one thing.
Okay, take a look at page 104. And that's kind of showing the changing model of your atom down in the bottom of page 104. There's a couple other key ideas with the differences between those two. So they do both have a nucleus, and to that point we did discover the proton and the neutron. So what else is different between your Rutherford and your Bohr model? What's different in the picture? What do you see, Jackson?
Like, the things, like in the Rutherford, the little gray things like going around it, and the Bohr model, there's like all spread, like the levels.
Okay.
Electrons.
We need to be a little bit more specific in our terminology. So yes, but what are those called? What's the difference?
The Rutherford, the electrons are like orbiting, I don't know what it is. They're like circling around it, and in the Bohr, they're just kind of all in like a different orbit.
What?
I don't know.
You just said it.
Orbit.
Good, these are your orbits, but they're your principal quantum number, which is your
Your energy level.
levels. Okay, so notice your planetary model, they're just orbiting in one area. Whereas in the Bohr model, we have specific what? What are those called?
Energy.
Specific energy levels that they're orbiting on. So that's your difference between the Bohr model. We have this quantized energy. You have these specific orbits that the electron has to be in as it's orbiting around your nucleus. Good. Next. What is ground state, Brian?
Is the lowest possible state of an electron.
Good. Energy level of your electron. Excellent. What is the uncertainty principle? Do you remember, Anna?
Let's see, it's like you can measure both like momentum
Mhm.
and position and all that stuff.
Good. Why not?
Because if it's moving
Mhm.
constantly, you can't measure where it's going to be, because once you measure it, it's going to be somewhere else.
Good. Or as soon as we find how fast it's going, it's going to be somewhere else. Or as soon as we know its position, its speed's going to change because of how small it is as well. Good. And then just reviewing some ideas for your quiz. Your quiz will be the next time that we meet, so be prepared for that. And what were the pages that I gave you? Okay. So dealing with your quantum numbers. Your quantum numbers is telling us the electron configuration. Big idea. What is electron configuration, John?
Electron configuration is the total arrangement of all of the electrons in the
Good. Your quantum numbers are different. What are our quantum numbers then? Sam, do you know? Okay, let's look at your periodic table. First of all, let's get our electron arrangement for neon. So neon, find neon on your periodic table. Electron configuration, I want all of the electrons where they're located for neon. Did you find neon? Okay, so we're going to start on your first row, and we keep going across until we hit neon on here. So your first row is your first energy level. What orbital's on your first energy level? S, which is what shape?
Spherical.
Spherical shape. So I have one S, and I have 2 electrons in that spherical shape. Then I go down to the next row. What happens when I go down to the next row?
Second.
Second what?
Energy
Energy level. Okay, so now we're on the second energy level. What's the orbital that's being filled first? Right here.
S.
2s, and I have 2 electrons in that second one. Then I move over to here. Which orbital is this?
P.
The P, the dumbbell. And neon has how many electrons in that? 6. Okay? Which rule states that your orbitals, you're going to get 1 electron filling or going across. So for instance, with your, as soon as I get to boron, I have 1 electron moving in here. And then when I get to carbon, I don't get another electron moving in this orbital. Where's that going to go instead? Whose rule is this? They're going to go in a different orbital until they pair off. So then it's going to go into this orbital. So I have 1 electron here and 1 electron here. And then your third electron is going to go in this third orbital. So I have 1, 1, and 1. And then they're going to pair off. Whose rule is that? Hund's rule. We also have what principle that tells us the specific order in which our electrons are going to fill? The off-law principle. So we're saying that the higher energy levels are going to fill before you get to your lower ones. So this is your electron configuration of neon in particular. Travis?
So how did we get the 6?
Okay, because we're going, this is the P block, so it's 1, 2, 3, 4, 5, 6 for neon. Because it's the noble gas. So if we were to look at it here on our actual electron shell, your first energy level, we have 2 electrons here. Okay, so the principal quantum number, what does that tell us?
The energy level.
The energy level. And What tells us how many electrons are on each energy level? Do you remember? How many electrons are on each energy level? There's a formula kind of with that.
2n squared.
2n squared, okay? So that means that on my first energy level, I can only have 2 electrons. And so it's in that s orbital, which is your subshell. What's the next quantum number tell us?
The shape and type of subshell?
The shape and type is the second one. The third one tells us the
orientation
in space. Okay? So we have these two right here. Then I'm going to get this second energy level, I'm going to have my s orbital filled. But when on my second energy level, how many total electrons can I have?
2.
2 squared times 2, so 8 electrons. So on my second energy level, these are my 2 s ones. Then I have 1 filling in each of the dumbbell. What letter is your dumbbell shapes? What letter is this? Which subshell? This is letter P. So I have 1 filling in each orbital. Whose law is that, Sam? Hund's rule. Before what? What happens next? They have to... What's going to happen next, Brian? So going across, I get 1 in each orbital. So 1 orange, 1 pink, 1 red. Before what happens? Travis, do you remember?
What was the question?
Okay, what's happening next? Jackson?
They jump to the next.
No, not yet. Okay, let's look at Hund's rule. What's Hund's rule saying? We get 1 in each orbital, 1 in each shape. Then what's happening after that? Do you remember, John? Did you find it, Travis? What page are you on?
I'm on 108.
108. Okay, did you find it?
I mean, is it pairing?
Good. So then, when I get the next one, these 2 are going to pair together. These 2 are going to pair together. These 2 are going to pair together. And this is your electron configuration of your neon atom. That's where they're located. That's what we're going to find. So the third, we still didn't answer that. What does the third quantum number tell us about if I wanted the address for this one electron? I know it's on the second energy level. I know it's in the p orbital. And then the third energy level tells us the orientation. So is it left, right, in and out, up and down, okay? And then the last one tells us your what?
Spin.
The spin of that electron. And what happens with your electrons, the reason why I draw them paired together is because the opposite spins, opposite magnets, what do? North and south magnets, they attract each other. And that attraction, if you have these unpaired electrons, that's what makes them magnetic, because your electron configuration tells you those physical and chemical properties of an atom. So those are your 4 quantum numbers. What are the 4 quantum numbers telling us? What do they tell us, Brian? Ben, what are they telling us?
The energy level, the shape.
Okay, all together. So you're being specific, but all together they're giving you the... Jillian, you have
Properties of the electron.
the address of one specific electron. Okay, so the electron configuration is determining your chemical and physical behavior of that. Yes, Anna?
Okay, so on the first energy level, when you have the 2 E's together, that's the S. That's the S.
This is on the first energy level, the s orbital.
Okay, so then when you went out to the second one, the 2 E's that you put down first were the S,
Mm-hmm.
and then the next 3 did the.
Mm-hmm.
So if you were to go another orbital out or whatever, would you go do
Into
S?
the next energy level?
Energy level.
Right, they always fill in that order.
Then you go S first.
S, P,
And then you would start with
and then
D.
we're following this, but what happens is you get S and then P, but then I actually get 4S2, and then I get 3D.
So you do S then D.
Well, that's what the off-ball principle is stating. The higher energy levels are going, so even though 4S is on a higher energy level, the 3D orbital, those have more energy than the 4S. So the order, that's what your off-ball principle is stating, that it's going to fill in this order. So instead of doing neon, if we did krypton, so find your periodic table, we had to go down another row. So you get 3S2 and 3P6. Then I have to go down to the 4th one, and that's that H on the other one. You have 4S2, then I have 3D10. Even though this is the 4th energy level, it's really 3, because on your 3rd energy level, you can have 3 shapes. You have the SP and the D, but it doesn't fill until you have 4S2, and then 3D10. And then going across to get your krypton, you have 4P6. So the D is going to fill before the 4p6. Travis?
We're gonna have to do that on the quiz.
Not on the quiz.
What about on the test?
So your electron configuration is determined in an atom's chemical behavior, with these orbitals, with this electron configuration, with your chemical reactions, we're going to focus on your outermost electrons. What are your outermost electrons called?
Valence electrons.
Valence electrons. Your valence electrons are just your S and your P. So notice so this is neon. Neon is that group 8. So what do we call neon? That group 8. They don't really react. Nope. Far right hand. I think you said it. What is it? It's a noble gas. Okay. Noble gases do not react because they have this full outer shell. However, if I go to the very next one after neon, which is sodium, sodium has one electron here. And this sodium atom is very likely to give up this one electron to another element so that it has a full outer shell on a lower energy level, but it has a full outer shell. This is how they're reacting. This is why they react, especially with water. Explosively react in order to get that full valence shell. So this is what's happening with your outermost electrons. Those valence electrons, they're trying to get 8 to get that full outer shell, which is your S and P orbitals. And we can see, or we can predict how they're going to react because of their valence shell, and well as show us our Lewis symbols for your valence electrons. So Lewis symbols are only for your valence electrons. How many valence electrons do we have? 8. Okay. So with your Lewis symbols, and so for instance, if I had this element, how many valence electrons does this element have? 5. Okay, so just 5 dots going around. Okay, now find your periodic table, and let's find sulfur. Find sulfur in your periodic table.
Found it.
What number is it?
16.
Okay, so the atomic number 16. What group number is it in? And that will tell you how many valence electrons it's in. Where's this periodic table?
Whose weapons for 115?
Okay. Okay, sulfur, what group is sulfur in up at the top?
16.
16. Notice underneath the 16, there's Roman numeral 6A. That's what I was referring to before. That 6A is telling you how many valence electrons it has. So sulfur has how many valence electrons? 6. Okay, so to draw the Lewis structure, draw sulfur. The first 2 dots, where do the first 2 dots need to go? John, you remember?
The first 2 dots need to go on the right hand.
Okay, so I have these 2 right here. So I have 1, 2, and then where do the next ones go? Bottom, 3. Next one?
The left.
4,
Top.
5, and then 6 down here at the bottom. And again, that's your Hund's rule that we're seeing with that. So that is the correct Lewis structure for sulfur. Okay, let's do a couple more practice ones. I want you to do germanium and calcium. And do those on your paper. Germanium and calcium.
Steel.
Yes? Okay, if you can't find it, you do have that alphabetical listing on your periodic table.
Calcium.
Okay, go back a page.
What were the 2 things that were the 2 elements?
Germanium and calcium. Brian, got a piece of paper? Okay, go back in alphabetical listing to find where they're located on your periodic table. Did you find where they're located? Got to figure out how many valence electrons they have, and then where do you put those valence electrons? Yes?
I know how many it has, but I don't know where to put the
Okay.
dots.
In your book, it has a 1, 2, and then 3, 4, 5, 6, 7, 8. And that's in some page on the book. Okay, so germanium. How many valence electrons does germanium have?
4.
4. Okay, so 1, 2, and then 3, 4. Calcium has how many? 2. It's your alkaline earth metal, so you have those 2 right there. Any questions on your Lewis symbols when I do those? Questions?
So you always put 2 dots on the right.
Okay, everybody take a look at page 110. 110. That's where it's showing you, it has the X, and it's this right here. That's telling you where you need to put your dots. So it's 1, 2, 3, 4, 5, 6, 7, 8, going around your elements. Am I in the way? Okay, so that's where that's coming from on there. Page 110, 111, it's telling you how a laser was developed. Now light, what gives off light? Why do we see light? What's jumping energy levels? Okay, your electrons are jumping energy levels, and that gives off light. And one particular form of light that we can use with a tool is a laser pointer. And with the laser pointer, there it is. Okay. So what's unique about your laser pointer is that you have this beam of light that's very concentrated and allows us to see that. Okay, I'll try to have a water bottle full with that, but have you done the water bottle? You can see the laser pointer through it. Okay, why does a laser pointer do that? And that's what's explained on the bottom of page 110. Whereas a flashlight, your flashlight beam, and light goes out like this. Okay, but a laser pointer is this laser or this beam, this concentrated light that we can use. Have you done it at night sky before? It's really neat to see, pointing out the different, you can see that whole beam of light. It's really, it's fascinating to see. But notice on page 110, what's giving off that light is you have those electrons are excited. And then when it's excited within this laser pointer, or then notice a photon strikes the still excited atom. What's a photon?
Tiny packet of energy.
Of light. Okay, so it's a packet of energy of light. So in this, we have this electron that's excited, and then we strike it with that beam with that extra photon of light, and this causes two photons to be emitted, and then the atom returns to the ground state. So you have this constant bombardment and this very direct stream of light because of this extra excited state that's happening within your atom, and that's what allows us to have this laser pointer, this direct beam of light. Why do we have different colors of laser pointers?
Because there's different light spectrums and like how strong each one is, I guess.
Okay, we're on the other ideas with this. Okay, why are we different frequencies of light though? So yes, it's different frequencies, but why? Different elements. So this is it's giving me the wavelength of max output. It's not telling me which element. But you have different energy levels and different elements that are used for them. You have a picture on page 111, the ship-mounted laser test system. The military uses this to guide their missiles, or if you've seen them with any type of hunting, you have that laser pointer to make sure you hit your target. Same type of idea with those. So very, very high. You'll notice the chemical reactions they're showing you down there. So we have one with AR. What's AR? Argon and fluorine. You also have one with the hydrogen peroxide and KOH. What's KOH?
Don't know.
K is what? Potassium. What's OH? OH negative.
Hydroxide.
Potassium hydroxide. And then your Cl2. That's another type of reaction, as well as the I2. What I2? I is iodine plus the oxygen. So those are the reactions that are giving us that laser pointer. They're giving us those characteristics of that. Okay? So now switching gears to chapter 8. So chapter 7, we studied light. Light showed us that electron configuration. What is your electron configuration? What is that? What is the electron configuration? So it's this, but what is that? What do all those numbers mean? Travis?
It is the complete arrangement of electrons in an atom.
Okay. How do we know that electron arrangement, or what does that information help us with? And that is how we really developed the periodic table. And that's the order that we saw in the periodic table. Why does it have this weird looking shape? And we noticed before, one reason for that weird shape is because it gives us different characteristics. Or this is representing which orbital? Which orbital is going to be filled with this? It's the white box. This is your S orbital. Over here is which orbital?
The
The P orbital. Right here, Jackson, is which one?
The D.
Okay. And then this one is your
F.
the F orbital. Okay, so that is one reason for that arrangement of your periodic table, but it was based on discovering different information about your elements. And the very first person was experimenting with elements, and he grouped certain elements, what we call triads. Well, triads means what?
Three.
Okay? So what he found was this element, and this element, and this element had characteristics that were the same, and he put them together. You'll notice on page 113, sulfur, selenium, and beryllium is what he saw. And then he saw these other three elements, and he put these together. So they were finding patterns. They were trying to find ways in which the elements could be grouped together based on similar characteristics. So this was John Dobenheimer, and he grouped in groups of 3. And notice sulfur, selenium, and beryllium, the average atomic mass of all 3 of those was 80. So he grouped his based on an average atomic mass. And the middle of each triad was very similar to the average of all 3. So notice the average was 80, and then selenium is the middle one was 79.4. Then he had chlorine, bromine, and iodine, and he put those together. And he had very similar characteristics. So Dobenheimer gave us groups of 3. What do we call those groups of 3? Triads. Okay, so he grouped them together based on similar characteristics. And he also noticed that arranging the known elements in order of increasing atomic mass, so the elements are getting bigger, we had similar properties with each element. And he called this arrangement the law of octaves. And an octave, if you're familiar with music, how many of you are, do you know what an octave is in music? What's an octave, Anna, do you know?
It's like every 8 notes.
Okay, every 8 notes, and we see this every week. What happens every week? What gives us the course of a week? A week starts on what day? Sunday. Okay, good. So the week starts on Sunday, and then what happens every week? It goes Sunday, Monday,
Tuesday, Wednesday, Thursday, Friday, Saturday.
and then what happens again?
Another week.
We have another week, and oh, look at that. It's what day?
Sunday.
Sunday, and then what happens?
Monday,
Tuesday, Wednesday, Thursday, Friday, Saturday.
Another week.
Sunday. Okay, so you have that week. So we see this repeating pattern. Okay, so for a week, how many days? Sam, we're done now. Okay. How many days are 1 week?
7.
7. Okay, same idea. With a week, you have that repeating pattern with a week. We see that with the law of octaves, but with an octave, we're saying every 8 for that. So he was calling this similar properties every 8 elements. So we had these triads, but we had similar groupings with every 8 elements that he called the law of octaves. Yes? Okay. Up at the top of page 113, you used to have a picture of Mendeleev's periodic table. Okay, so Dobenheimer gave us these groups of 3 called what? Triads. Okay. Then Dmitri Mendeleev took those same elements and he put those elements in characteristics, or he grouped them a little bit differently, and he put them in groups going down, and he noticed, and he was grouping them not by atomic mass, but by atomic number. What's the difference between atomic mass and atomic number?
Everything.
Yeah, what is that everything?
I don't know.
That's a big important idea. What's the difference between atomic mass and atomic number? What does atomic mass tell you? Well, what is mass?
How much the amount of matter.
Okay, so quantity of matter. What's the atomic number tell you? Okay. So we see these elements. So he was taking those and he was experimenting with them and he found these characteristics. And what is so amazing is that he took these different elements and on his periodic table, at this time we only had about 147 known characteristics or 147 known elements. But what he did with his periodic table, so he had this arrangement, but he left open spaces. So he knew, based on this arrangement, you notice 1, 2, 3, 4, 5, 6, 7, and then I think I had another color in here that's different. He had purple's on there, gray, there we go. This is that law of octaves that he saw them repeating. But these were the elements that we knew, but he predicted what would be the characteristics of an unknown element. So right here we have a missing spot. Based on the trends that he saw, he predicted this element would have this atomic number, this element would have this atomic mass, this element would have these characteristics. And that is one reason why we use Mendeleev's periodic table. His design of the periodic table was really just these 2 groups over here, this group and this group, and then further experimentation gave us more information of that. So it's really just those 2 groups together, but based on the way he organized the information, and this is that scientific method, he was able to predict. That's the purpose of experimenting. That's the purpose of finding those results and interpreting that data, is to predict, come up with a conclusion of what's going to happen next. So he predicted the characteristics of this missing element very, very, very accurately. Now, it wasn't exact, but it was so accurate, it was a very good prediction of what it was. And his predictions led to what we call the periodic law. Take a look at the bottom, page 114. This is showing the predictions that Mendeleev have. So notice this is EA. He called it Eka aluminum. So it's like a mimic of aluminum, is what he called it. But it's really the element gallium. Notice he predicted the atomic mass would be 69. The actual atomic mass was 69.7. The density, he said, was going to be 6.0 grams per cubic centimeter. The actual density, he was 1/10 off, 5.9 grams per cubic centimeter. So this is why Mendel's arrangement of the periodic table has stood the test of time, because of his predictions and how scarily close they were to the actual one. And he had another one, he called it Eka silicon, so this is like a mimic of silicon, but it was really germanium, GE, that we took a look at earlier. And you'll notice how very similarly close they were to what he predicted and what we actually see when we discover that element. That element wasn't even discovered yet, or they did not have the technology in order to just study it exactly for that. So the periodic table, the main credit for our modern development or modern arrangement of our periodic table was who? Mendeleev. Okay, so Mendeleev is how you pronounce that name. So Dmitry Mendeleev is who we have credited with our modern periodic table based on that. But we also see what we call the periodic law. And the periodic law is that the physical and the chemical properties of the elements are periodic functions of their atomic numbers. Okay, so what does that mean? Well, in a week is periodic. We have the same thing that happens at the same length of time. We have that pattern, which is starts on Monday, and then what's next? Sunday, and then Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Well, I know, beyond a shadow of a doubt, what's going to be next? Sunday. I know what's going to happen next. And this is the same idea with your law of octaves, but your periodic law, more specifically, we're saying that they're periodic functions of what? What does it say according to your textbooks? They're periodic functions of what? Since they're a periodic function based on the day, it's based on the, not atomic mass, but the, of their atomic, what is it? Numbers. So that is how our periodic table is arranged. What does the atomic number tell us?
The number of protons?
Yes, your number of protons. So, as we're going across in your periodic table, we have atomic number of 1 with your hydrogen and the atomic number of 2 with your helium. That fills the s orbital. That's completely filled. Then I'm going to go to the second energy level, down the next row, and you have the s orbital being filled with 3, 4, and then going across you have that p orbital, 5, 6, 7, 8, 9, with the atomic numbers increasing. And what happens when I go across, now I'm on the third energy level, but we see the group of these elements all behave the same way. The ones that are arranged this way, so I know that all of these elements, your alkali metals, are going to behave very similarly together because they're periodic functions of their atomic numbers. Each of the elements in this group have how many valence electrons? 1 valence electron. And what tends to happen with this 1 valence electron is it gives it away very, very easily to get full outer energy level, full outer shell on a lower energy level. Group 2, how many valence electrons do these have? 2. So we have 2 electrons here that it wants to give away. Moving over to this group, how many valence electrons do these have? 3. And they also have the same Lewis structure because they have the same valence electrons in the outer shell. So they tend to give away those 3 electrons. Carbon group,
4.
How many valence electrons? How many?
4.
4. So with those 4 valence electrons, this carbon is in everything that's alive. And it's because it's versatility. Do you remember your substituted hydrocarbons? No? Yes? Substituted hydrocarbon with your alcohols and your carboxylic acids and your esters. Okay, those are your substituted hydrocarbons. That's because carbon is so versatile. You have 4 valence electrons. It can either give away 4 or it will get 4 to make those different bonds, everything. Nitrogen group, how many valence electrons? 5. So it wants to gain 3 more to get that 8 in the outer shell, so it tends to have a -3 because it wants to gain 3. Your oxygen group, how many valence electrons? 6. So it wants 2 more. That's why we have that -2 charge. Your halogens, how many valence electrons? 7. How many more does it need to be 8? 1 more. That's why they have what charge?
Positive, negative.
Negative. 1, only a negative 1 because they want one more electron. And then your noble gases have how many valence electrons?
8.
8. So they do not react with those. So that is what we call your periodic law. The physical and chemical properties of elements are periodic functions, repeating functions going across of their what? Atomic number, which is the what?
Protons.
Number of protons. So again, with our modern periodic table, we see a trend with these different elements. So take a look at this graph up here, and there's two things I want you to do. I want you to follow this graph, so start with hydrogen, and then follow it on this periodic table that you have in your book. So the very first element in this graph, okay, so reading this graph left to right. Okay, what is this graph telling you? Notice we have atomic number down here on the bottom. What is atomic number?
Number of protons.
Number of protons versus molar volume. Molar volume is how much capacity it has. So comparing the molar volume to your atomic number. So the very first element on this graph, reading left to right, is what?
Hydrogen.
Hydrogen. So find hydrogen on your periodic table, hydrogen, and then following the line of your graph, notice it spikes upward, and we go up to what element next?
Helium.
Helium. Find helium on your periodic table. Going all the way across, it's over here. What's the next element following the line?
Lithium.
Where's lithium on your periodic table?
Under.
All the way back over here to hydrogen. What's next?
Beryllium.
I can predict the next element. It's probably going to be
Boron.
boron. Okay, do you see what's happening? What is this showing? What's happening with this? What is the trend? What do you see as trending? What is the pattern that you see?
It goes through one group and then
So
goes
as
through.
I'm going across a row.
Yeah.
Okay, so this is called a row. A group is vertical. So as I'm going across a row, what's happening?
It's naming off all the.
Okay, as I'm going across, what is this group, or what is this graph telling you that's happening as I'm going across? That's another big idea. That's interpreting this graph. So as I'm going across, what is happening? Okay, so first of all, what do you notice about the shape of the graph?
It changes a lot.
Okay, what is happening though?
It's going up and down.
It's going up and it's going down. So what is the trend? What's the pattern as I'm going across? What's the pattern? Did you find it, Anna?
Like, when it starts in your row, it
Mhm.
starts at very high, and then it starts working its way down.
Works its way down. Okay, but what does that mean in terms of your graph? Okay, so when I start a new row, so down here, when I start with, so notice potassium, start here. So notice I start at the peak, and then it goes down as we're going across. What does that mean, though? So what do the peaks and what do the low points mean on this graph? Well, what is our y-axis? What is the numbers?
It means it has less molar volume.
The molar volume. So here I have the highest molar volume here, and then as I go across, the molar volume, or your atom, is shrinking. The molar volume is getting smaller going across. That's what we call periodic trends, or what we're going to get into called periodicity. These are trends, these are behaviors. This is another reason why we have the periodic table arranged in that way. Okay, so now we need to be a little bit more specific. What is the arrangement of our periodic table? Well, going up and down, vertical columns are called groups. And we have been kind of referring to those already, but notice elements in the same column belong to the same group. And what we've noticed already, if they're in the same group, what's going to be true about their valence electrons?
So the same.
They're the same. Because their valence electrons are the same, on your periodic table, I can tell you the charge of that element, because they're always going to behave the same way. So group 1 tends to have what charge?
Positive 1.
Positive 1. Group 2A has what charge?
Positive 2.
Positive 2. And again, that's this block, and then going over to our P block. Group 3 tends to have what charge?
Positive 3.
Positive 3. Group 4 tends to have what charge?
Positive.
Plus or minus 4. Okay, so plus or minus because they can either gain or lose 4 electrons. Your carbon group tends to have what charge? Negative what?
5.
Not negative 5, but we have 5 valence electrons. I want how many more to have 8?
3.
I want 3 more, so I'm gaining 3 electrons. If I'm gaining 3 electrons, it's going to have what charge? What'd you put on your periodic table? It's a negative 3 because I'm gaining 3 more electrons. Your oxygen group is going to have what charge?
It's gonna have a negative 3.
Not negative 3, negative 2. And then your halogens are going to have what charge? Negative 1. So notice you go all the way up to 4, positive 4, plus minus 4, and then we go back down to negative 3, negative 2, negative 1. filling the outer shell. Okay, so your vertical columns, what are those called? Groups, okay? Then, going across a row, your rows are called what? Periods. Oh, would you look at that? That's why we have the law of periods. What is the law of periods? As I go across, what's your law of periods? What's happening as I go across? We see a trend. What's the trend? Brian, you see that? Go back a page. What's the law of periods? As I go across, what's happening on your periodic table? How are they ordered? Why are they put in that specific order? What's happening as I go across? It's 1, 2, 3, 4, 5. What are those?
Numbers.
The groups.
Yeah, what are those numbers? They have a specific name. What's that number? Okay, so look at your periodic table. Hydrogen is 1. Helium is 2. What's number 3? Lithium. What number am I referring to? What number? The number of protons, which is the atomic numbers. Okay, so as I'm going across, we see this periodic trend. What's happening to your atomic number? It is increasing. So that is your law of periods. We see this trend. The physical and chemical properties of elements are periodic functions of their atomic numbers. So certain groups behave the same way. And on your periodic table, there's a couple of different ways that we can classify your elements. Okay, one is classification is based on their metallic character. And this is what we did at the beginning of the year with your coloring on your periodic table. You have 3 different types of elements on your periodic table. You have your, and this is on page 115. The blue is what? What does the blue represent? Metals. Notice most of your periodic table is blue. Therefore, most of our elements are
Metals.
Metals. Okay, so most of our elements are metal. Then we also have the orange diagonal. What is the orange diagonal?
Semi-metals.
Semi-metals. So there's somewhere in between. And then we also have the yellowish greenish color, which is the
Non-metals.
So one way to classify our elements are based on their metallic character. Are they a metal, a semi-metal, which is also a metalloid, or are they a non-metal? So that is one way that we can classify our elements based on that. And with these elements, we can also show what we call the representative elements or our main groups. Take a look at the top of page 116. This is the long version of your periodic table. And just so we can condense it into that sheet of paper, this is what it would look like if we didn't have that lanthanide and actidide series down here. This is what your periodic table would look like. See how long it is? Because we're including that F block in the middle of your periodic table for that one. But another way that we can classify these is based on what we call your representative elements or your main group elements. And that's what these color coordinations are showing you at the top of that. You can see the green, the first column, are your alkaline metals. The second group are your alkaline earth metals. Right here is the inner transition metals. So those are your inner transition. Your D block, those are called your, do you remember? Transition metals. Then you'll notice kind of the P block, the carbon to oxygen group, they don't really have a name, but the second to last group, group 7A or group 17, those are called the orange, because your halogens in the very last group are called your noble gases. So that's another way. These are called your representative groups, and they're grouped together because they have similar characteristics within that group that you have characterized for those. Okay? So let's stop there for today. With that, what do we call a column on your periodic table?
Group.
Column is your group. What is going across your row is your period. Who gave us the modern version of our periodic table? Mendeleev. Who gave us the triads, the groups of 3?
Something.
Dobin. Okay. Gave us your triads. What states that the physical and chemical properties of the elements are periodic functions of their atomic number?
Periodic law.
Periodic law, where every 8 elements we see a repeating pattern that is called your law of octaves. Law of octaves for those. Why was Mendeleev's periodic table accepted?
Because it was so close.
Because he was able to make predictions.
It was so close.
For the elements that we don't have for those. Okay. I'll So your homework tonight, your quiz is going to be, what hour? 5th hour. Okay, so 5th hour we have us again. You'll be taking your quiz then, and then I'll give you your homework that hour since you're not going to have time to work on it between there anyways. Okay, so that will be our normal class hour. We'll be taking your quiz.